Alright, so today we're going to be discussing oxidation numbers, and we're going to find out how you calculate and assign oxidation numbers to ions. So the first element we're going to look at is iron. This is a normal common element that we all know of. It's hard metal, transition metal, right there in the middle. It's used to form steel. It has many purposes, and this is iron. But what about iron 3 plus and iron 2 plus? We see these appear differently, but what's the difference between them? The difference comes, we have to look from our oxidation number, which is always denoted by a superscript number and symbol in the top right portion of our either the ion or the compound that we're dealing with. So in iron 3 plus's case, it has a positive charge of +3. That's why there's the 3 in the plus. Now this means that it's positive by 3, and we know that electrons each have a charge of -1. So that means that our iron 3 plus here has lost 3 electrons. That's how it became positive. So when we look back at normal, our standard state ion, we look at the periodic table, we see that it has 26 electrons. Now, because this iron here lost 3 electrons, we see that it now only has 23 electrons as opposed to the normal 26. If we look further at our iron 2 plus, it has a positive charge of +2, which is denoted right here, and it has only lost 2 electrons in comparison with standard state, or we could say that it's gained 1 electron as opposed to our iron 3 plus. Our iron 2 plus has 24 electrons as opposed to the normal 26. But what does that mean? This means that if we put it in solution, if we're going to have this in a reaction, we're going to react with something, our iron 3 plus here is far more readily reducible than our iron 2 plus, which is much more likely to be oxidized than it is to be reduced. We can tell this, we look at our standard reduction potentials here, our voltage. We see the iron 3 plus has a 0.77 voltage as opposed to the -0.4 voltage that is with our iron 2 plus. So Fe3 plus much more readily reduced, and our Fe2 plus is much more readily oxidized. But now we're going to look at how you calculate and assign these oxidation numbers, because most of the time, they're not always given to you and expressly stated, and you'll have an element or a molecule that's within a much larger ion or compound. So when we want to find the charge of our molecule here, we're going to look for our base molecule, and the way that we find the charge of this base molecule is we have to use common molecules that are going to be added to form our ionic compounds and complex ions. Now, the common ones that we find are hydrogen and oxygen. These are most commonly found here. Now, this is not always the case, but for right now, we're just going to assume that hydrogen always has a charge of 1 plus, which we can see is denoted again right here, and our oxygen is always going to have a charge of 2 plus. We're going to use 2 minus, excuse me. We're going to use these charges in order to calculate the charge of our base molecule, which is what we want to know. So, our first example, we're going to look at a permanganate ion. Chemical formula is right here, MnO4 1-. So, what we want to do is we want to take this chemical formula and we're going to break it apart and form a mathematical formula, because that's how we're going to solve for the number, and the number, of course, will become our charge. So to break it apart, we're just going to separate everything. So over here we have Mn, or manganese. And this is what we want to solve. We don't know what it is, which of course in math we all know is represented by x. So we're going to change our Mn here to x. Now we're going to break apart our O4. We have 4 oxygens. Well, as a variable O, we know in math that we don't use these subscript 4s. So we're going to change this to 4O, as in we have 4O, whatever O is. Now we look up here, and this is probably our most important number here. And probably if you're looking at a problem, this is where you're going to get it wrong, is because you're going to forget about this little guy up here, our charge of 1-. This is the overall charge. Everything that's in here, when you put it together, is going to equal 1-. So we're going to pull that apart, and we have 1 minus. But of course, 1 minus is a scientific term and not a math term, and we're trying to make science into a math formula, so we're going to change 1 minus to -1. So now moving forward with our permanganate ion, we're always going to add to equal the overall charge. So everything in here, we add. We always use addition, no matter what, 100% of the time, we use addition to equal this charge right here. So back the way we have them split apart, we can see this right here. X plus, always adding, no matter what, we're going to add. X plus our 4 O's is going to equal our charge of -1. But now, in this case, we have 2 variables, and we can't have 2 variables. So what does O4 equal? What does that mean? We're going to pull this over here, and we know that each oxygen has a charge of 2 minus, and we have 4 of them. So very simply, we're going to multiply 2 minus by 4, giving us a charge of 8 minus. Once again, just as we did with our charge of 1 minus, 8 minus is a scientific term, and we're not dealing with that right now, so we need to make this a math term. Simply flip the sign in the number, and we're going to get -8. So our equation now becomes x minus 8 equals -1. And now we have an incredibly simple algebraic expression that we can use to solve for x. We quite easily see, as we add the 8 over, we see that x equals 7. This is a positive 7, so we put this as our charge. Remember, x represents our manganese over here, which is what we want to know. Our manganese simply has a charge of 7 plus. We add this plus here because our 7 is positive. Had this 7 been negative, we would have written 7 minus. So let's look at another example. If we have a molecule of ethanol, ethanol C2H6O right here, in the same case, this one's a little bit more complicated because we have more elements and more ions here. So we look at the charge in. The first thing we're going to notice is that there is no overall charge written in our top right hand of the ion, or molecule, excuse me, in this case. So what does that mean? That means that we have a charge of 0. If nothing's written there, no pluses or minuses, the overall charge is 0. And once again, like before, we're going to equal 0. And we have 3 things here. So our equation that we have so far is something plus something equals 0. So let's look at our first element here. We have 1 oxygen. Well, we know that our oxygen is worth 2 minus. It's always worth 2 minus. 2 minus, we're going to convert that to -2 as we have a mathematical term. Now we have something plus something minus 2 equals 0. Move on to our next element here. We have H6. That means we have 6 H's, which we would write as 6H. Each H we know has a charge of 1 plus. So what we're going to write is something plus 6 times 1 minus 2 equals 0. Remember, this 6 is coming from our 6 on our hydrogens up here. Now, we're going to look here at our carbon. Carbon's what we don't know. This is what we want to find. So once again, we're going to represent this by X. But unlike our permanganate ion, we have 2 carbons. That means we have 2 of our unknown. So we're going to write this simply as 2x, of course. Put this down back into our equation. We have 2x plus 6, which of course is our math we did up here. 2x plus 6 minus 2 equals 0. And once again, we have a readily solvable algebraic expression, which we're just going to solve for x. And of course, we add our 2 over, subtract the 6, get -4, divide -4 by 2. We see that x equals -2. Flip the sign and number, and we see that our carbon in ethanol has a charge of 2 minus. And that's it.